Hi there, I'm Nick Karpowitz from the Max Planck Institute of Quantum Optics in Garching, Germany. And normally on this channel I've been posting tutorials for my open source nonlinear optics code, but today I thought I'd try something a little bit different. So my research group looks into ultrafast optics and attosecond physics, and so we had a paper come out today that I thought would be interesting to talk about. So here's the paper. It's in the June issue of Nature Photonics. I'll have a link in the description, and it's open access, so you don't need a subscription to read it. So maybe first I'll unpack this title a little bit. So field resolved attosecond solitons. Field resolved means we are measuring the electric field of light. Maybe you've used an oscilloscope before, which lets you measure a time varying voltage or electric field, typically in the megahertz or gigahertz spectral range. In this case, we are measuring a time varying electric field in the hundreds of terahertz range, so visible light and maybe into the petahertz range, ultraviolet light as well. This is one of the things we do. We like to make techniques for detecting very fast electric fields. So we have a technique that we think works, and then the next step is you need one of these very fast electric fields in order to measure it to test if it actually works or not. So this is where the attosecond soliton part comes in. So what is a soliton first? A soliton is what happens when you have a balancing between linear and nonlinear propagation effects. It happens with light pulses, for example, in optical fibers, but it can also happen in water waves, things like that. So if you have a localized oscillating field, a pulse, normally you send one of these things through a medium, and not every frequency of oscillation will propagate at the same speed. For light, you have a different refractive index for different wavelengths. So if you send in a pulse, which is made out of a bunch of different wavelengths just overlapping together, the different wavelengths that make up this pulse will spread apart in time. So your pulse will get stretched, it will just fall apart as it moves through the medium. However, if you add a nonlinear effect to this, so in this case, self-phase modulation, what this does is it changes the spectrum of the pulse as it propagates. And it does this in such a way that the linear effect, which is trying to pull, say, red wavelengths behind blue wavelengths, will be counteracted by this nonlinear effect, which is putting red wavelengths in front of blue wavelengths, roughly speaking. So you have a balancing between these two effects. And this produces, in the lowest order, what we call a soliton. So the fundamental soliton will be a perfect balancing between these things. And you can have a pulse which will just keep the same temporal profile as it propagates through the medium. We use what's called a higher order soliton, which can shrink and grow, and we let it shrink in the first place. So we've been following very interesting research by others in this field, especially John Travers and Harriet Wad. And so you let the pulse shrink, and it shrinks to a surprising degree. So we start with a 3 femtosecond pulse, and it shrinks itself below a femtosecond. And a pulse below a femtosecond, an attosecond pulse, so 1 attosecond is 10 to the minus 18 seconds. It's a difficult thing to measure. So our pulse is not a single attosecond, it's a few hundred attoseconds, but it's a few hundred attoseconds in the visible and all the way to the deep ultraviolet spectral range. So a very short oscillation of light as you see here. So measuring this is tricky, but luckily we had a technique that we wanted to test out, right? So these two things sort of have to come together. If you want to know that you have a very short laser pulse, you need a technique which can actually measure this very short laser pulse. And if you want to test a technique that can measure a very short laser pulse, you need a very short laser pulse to try the measurement. So this was Amelie Heinzerling's PhD project to sort of work out this puzzle. So you need both of these fairly difficult things to work at the same time. Here she is working on the setup. And you can imagine that this is also a fairly tricky thing to work with. Inside of this vacuum chamber, there is a glass fiber, which is supposed to guide a fairly intense laser pulse with 10 atmospheres of pressure of helium on one end and a vacuum on the other side. So the full details of the experimental setup are in the paper, but you can imagine it was kind of a challenge, but it worked. She actually finished her thesis, graduated last year. Just there's always a bit of a lag before things are published. And so this works. We see this incredibly short laser pulse, so less than 400 attoseconds long if you measure the duration of its intensity. We are looking forward to actually using this stuff in our research. So what we like to do with these field measurement techniques is make use of the fact that if you have light interacting with matter, say you want to investigate how electrons in a solid respond to an intense and short light pulse. Well, the electrons will get excited, they'll move around, and this excitation and moving around of electrons, you can describe this in the form of a current. But we know from Maxwell's equations that if you have a time-dependent current, it will radiate an electric field. And this electric field then modifies the laser field that was doing the interaction. So we can actually pick out a pretty detailed history of this interaction through subtle changes in the electric field of light. So that's what all of this stuff is for. So I hope this is interesting, and maybe you're interested enough to read the paper. And if you do and you have questions, feel free to ask them in the comments below. And in any case, have a nice day. You can do the YouTube standard clicking on buttons thing if you want to hear more videos like this. And have a nice day. Ciao.